Hello everyone and welcome to my channel. This is Sohini from South Bay, California, and I welcome you today. So today I am going to be introducing the concepts of conversational AI using Nvidia's very recent Jarvis. What is conversational AI? Well, that's how you have conversations with any virtual assistant, say it your phone or your car, or you know what? Let me show it to you. So this is Sohini, and this is her digital assistant S. Hey S, define conversational AI. What is it? Conversational AI or artificial intelligence refers to technologies like chatbots or voice assistants which users can talk to. They use large volumes of data, machine learning, and natural language processing to imitate human interactions, recognizing speech and text inputs and translating their meanings across various languages. And this definition is according to IBM Cloud. Okay, S, can you give me some examples of conversational AI? Most common examples are interactions with virtual assistant. Watch this example.
Is it snowing in Chicago right now?
In Chicago, it is currently not snowing.
I'm actually planning to visit there.
That sounds like a lot of fun. What else are you planning to do while you were there?
That's interesting. I see that the virtual assistant figured out the context, which is Chicago in this case. So this would really help quicker information retrieval. Can I have another example? Hey S, can you give me another example, please? Sure. Here is another example of automotive virtual assistant helping with navigation.
Find us a Mexican restaurant.
The nearest Mexican restaurant is Luna Mexican Kitchen, located at 1495 the Alameda, San Jose.
How's the weather in San Francisco?
It is currently 66 degrees and sunny in San Francisco.
Actually, you know what? I'm kind of feeling sushi.
Really?
Yeah.
Alright. Show us a Japanese one.
The nearest Japanese restaurant is Aniki Sushi, located at 3810 Mori Avenue, Fremont.
This was great. I now see that the system can automatically figure out contexts such as a restaurant and also weather in San Francisco. This would really help to have human-like interactions. What are the other components of conversational AI, S? Yes, there are other components of conversational AI, namely automated speech recognition, ASR, for text-to-speech, diarization, speaker identification, natural language understanding that includes content summarization, natural language generation to formulate a response, text-to-speech or TTS, and reinforcement learning to improve the performance over time. Well, that was amazing information. I'm interested in learning more. Let's learn about the conversational AI components in the next segment. If you like what you see, and if you are interested in learning about more use cases of AI and introducing these concepts early on to you, please give this video a thumbs up and subscribe to this channel. Now that we understand some of the use cases for conversational AI, let's look into the components of conversational AI with specific examples from Nvidia's Jarvis. So conversational AI, as we have seen, has three major components. First off, we start with automated speech recognition, or ASR, which has a typical example such as this.
Well, if you like, I can set you up with an optometrist to get an eye exam.
That'd be great.
Okay, no problem. We'll get you started with that.
The major task of automated speech recognition is to take the speech that we're saying or the audio stream and to convert it into text. And some of the major challenges in this area is sensitivity to language, to dialect, as well as to jargon. So the Jarvis that has been released, it actually has a medical component to it as well as a normal dialect, so that if you're talking about medical jargon, then it's going to be more sensitive to those kind of verbiage as opposed to normal language. And it can also be retrained for something more specific, such as mathematical equations per se. The second component for conversational AI is audio processing. Of course, as the audio stream is coming out, there is the need to do speaker diarization. So understanding which speaker is talking at which exact timestamp. And that is done using the Mel spectrograms typically. The other task here is emotion recognition. Typically, getting emotion from text only is actually a pretty hard task. So that's why audio processing and emotion recognition from the audio stream itself and combination of language along with the audio streams has been found to be more profound and more accurate for emotion recognition. And then finally, the third task, as we all know, is natural language processing that has two major components of content summarization or natural language understanding. Of course, there is named entity recognition, which is understanding major nouns. If you're talking about an eye exam, if you're talking about ophthalmologist, if you're talking about a place, person. So these are named entities that you want to recognize because that's what sets the context. And of course, there is natural language generation, or in this case, the response generation. Let's look at these three components in a little more depth. So the major methods and models for ASR, for automated transcription, include feature extraction, which is typically using the Mel spectrograms. Then there is acoustic modeling, followed by language model decoding. Now let's look at these three components separately. Now the acoustic model typically here has the highest complexity. So if you're able to ensure that you have a least latency or least complicated acoustic model, you will get a much better end-to-end response time for the overall transcription in this case. Now typically there are decoders that compute the most likely word sequence for an audio input, and that is typically done using either a beam search or a word lattice. Let me give you an example for this. So let's say that you are trying to you're in a foreign land and you are searching for water. So if you ask for water in your own native language, then the foreign language translation for it, that would be the decoder that we are talking about in this case. And of course, language can happen. It's a sequence of words, right? So the most accurate sequence of word is the one that needs to be transcribed or printed out as the most likely sequence. Now word lattice typically is represented as a weighted finite state transducer as well. Now let's look at the acoustic model, because that is the most limiting condition, or like you mentioned, that is the part which is the most complex. Now one of the major ones that are used right now is called the Jasper acoustic model, and again the link to that paper is again given in the description box below. In this case, what you do is you do an end-to-end speech recognition model, and this deep learning model, of course, uses 1D convolution. Of course, there are residual connections in order to ensure that enough signal is getting transmitted from the source to the destination, and the deepest version actually has 54 layers. And this paper, the authors actually claim a word error rate of 2.95 using the beam search. Now the beam search is actually the language decoding model which gives you the most likely machine translation sentence that should come out. So in this case, they are reporting a word error rate of 2.5% only. Another well-known acoustic model is called the QuartzNet. Again, the paper is in the description box below. And in this network, what happens is, again, there are one-dimensional time channel separable convolutional layers and of course residual layers, and this paper reports word error rates for 2 to 4% for clean data and 7 to 10% for other kinds of data. So these are the two different acoustic models that the Nvidia system actually handles. And of course, then there is GPU accelerated offline speech recognition, or in this case, this is the decoder. So you can either use the acoustic models with a normal beam search or a greedy search. Typically, beam search is more accurate than greedy search. But in this case, you can also use the GPU accelerated decoder, which enables much higher accuracy for your language models. Now let's look at the second component, which is your audio processing. So what are the typical methods and models used here? So the first and the foremost, the goal is to do speaker clustering for diarization. What does that mean? So let's say that you have an audio stream where multiple people are talking. You really would like to know at exactly what timestamps did which person start talking. And typically this process involves feature extraction, and again we use MEL spectrograms in this case, followed by clustering. So if there are, let's say, 4 different speakers, then you will see 4 major clusters that come out in the feature space if you have extracted the features correctly. And then you can classify these clusters for emotion, for speaker, and also typically you can cluster them for, cluster the audio stream for questions, commands, assertions, and exclamations. And this will actually help much more accurate and much more richer content summarization if it is done with the natural language processing along with audio processing. So typically the MEL spectrogram is extracted using FFT or fast Fourier transform. So you take the whole input signal, and then there is a windowing that happens, because of which you get this finite FFT length, and then you look at these signals in the frequency domain. Other audio classification resources also available in the description box below are given in this link. Now let's get to the final component, or natural language processing. So far you've seen that first of all you process the audio, you then convert the audio to text, but then what? Then comes the key piece, which is NLP, and in this case the first thing you need to do is a word to vector transformation. So each and every word now can be represented as a vector notation, and typical vector notations for that are pretty highly used, first of all, is fast text. Again, it gives a 300 dimensional vector corresponding to each and every word. And also then there is the glove. These two are the typical word embedding methods in which you can actually generate vectorized formats for individual words. And then you apply sequence to sequence models, so it's also known as seek to seek, which inherently uses recurrent neural networks, and beam search versus greedy search in order to decode the best sequence of words. So let's take an example in which we are trying to do a Hindi to English conversion. So the original text that goes in is मैं प्रकृति का आनंद लेती हूँ, and here you want to actually convert it into English, which is I enjoy nature. Now what typically would happen is, if you would just do a greedy search, it would find individual words which is the best match. So for मैं you would get I, and then prakriti would be nature, and then anand would actually be enjoy. So typically the outcome, if you just did a greedy search, it would be I, nature, enjoy, which doesn't really mean much in English. So in order for you to actually have the whole word sequence make sense in the language in which it is getting transformed to, that's why the lattice-based decoding methods are most accurate. And again, the next step is content summarization. I found a great article that actually looks into these RNN based methods in order to now do content summarization, and there you can actually get whole abstractions. So if you have a huge paragraph, you can actually extract the most relevant sentences from there in order to summarize a whole conversation into very key points, which actually helps your information storage and retrieval, and also then text to speech conversion, which is the response that gets generated out of the system. So next, I wanted to introduce the Nvidia Jarvis's open beta platform, which is now completely open to anybody who wants to use it. Again, it's an end-to-end train toolkit, and it is doing a lot of transfer learning. The models are already pre-trained. You can start with the pre-trained models, or you can also leverage complete training from scratch. And again, you can deploy services with Kubernetes and Helm using the Nvidia GPU operator. Typical specs for the speech recognition, for speech synthesis, and for NLU are given here. And again, this slide deck will be shared. So if you want more information, please go ahead and download it. And finally, I would like to say NVIDIA's, this Jarvis platform is now completely open, and it is for anybody to try out. You can now actually train your own transcription service, or you can actually train your own intelligent chatbot in order to, to take text, to quickly transcribe it, understand emotions, categorize, these things online or offline, and report back. How do you like the experience? If you like the video, please give it a thumbs up and subscribe for more.